So our next topic is going to be 6.1 and 6.2. We're going to look at roots and radical expressions, and then we're also going to look at multiplying and dividing radical expressions in 6.2. So before we get into it, just a quick review of some of our exponent rules. If we have like bases, right, here in number 1, a to the x equals a to the y implies that those exponents, x must equal y if they're like bases. When I divide like bases, a to the x divided by a to the y, this is equivalent to a to the x minus y. I subtract those exponents. Similarly, when I'm multiplying like bases, we add exponents. Anything to a negative power moves that particular term into the denominator or from the denominator up to the numerator. If I have a power raised to a power, so let me write this, a to the x all to the y power, right? A little bit more clear than in the slide there. When I have a power raised to a power, I multiply exponents. And the last one we kind of do here, or the next one we do kind of in the other order. If I have a quantity, and by quantity I have a product, right? Or division as well. If I have a times b or a divided by b, all raised to a power, I distribute that power to each of the individual terms. However, if I have a sum or a difference, if I have a plus b, I raised to a power, I cannot simply distribute that power to each term. It does not work like that. All right. 8, anything to the 0 power equals 1. Anything to the first power equals itself in 9. And 1 to any power equals simply 1. So what is a root? All right, so a root, we're talking about any real numbers a and b and a positive integer n. So if I have a to the n equals b, then a is an nth root of b. Okay? So I can also write the nth root of b is a. All right, so an example here, if I had, let's do 4 squared. Since I know 4 squared equals 16, I then also know that it implies that the square root of 16, right, equals 4, right? And for a square root, we never write the index. If it's not written, it's implied to be 2, but the index will go right here, and we're going to talk about that here real soon. And again, this is true because I have a square root. 16 can be written as 4 squared, right? And the square root and the square cancel, leaving me with the 4. All right, so the 4 to the second power equals 16 is somewhat equivalent to the square root of 16 equaling 4. They imply one another, okay, thus an nth root. So another example using some higher powers here. If I have 2 to the third equals 8, and therefore 2 is the third root of 8, and thus the cube root of 8 equals 2. So if I have a cube root, then I'm looking to be able to take this 8 and write it as something to the third power so that I can simplify. And here I get 2. Right? Also notice that 2 to the fourth equals 16 and negative 2 to the fourth also equals 16. So we have that 2 and negative 2 are fourth roots of 16. Right? So the fourth root of 16 could be either positive or negative 2. A little bit of terminology in terms of radicals. Right? The radicand is this part inside of or underneath of my radical symbol. The index of the root tells me essentially what power am I dealing with, right? Am I dealing with the square root, third root, fourth root, so on and so forth, right? This is typically written, or should be written, right up here, okay, when we have a radical. What's really important is you write it so it almost looks like an exponent in front of that radical symbol, because if you write it like this, I'm going to think it's n times the square root of a. Make sure that you have it written up here so that it's clear that we actually have an index and not a number times that a. Okay, so just make sure you have that distinction down. So let's go through, let's do a couple of examples here. So if I have the square root of 16, right, what number times itself equals 16? It's going to be 4 squared, right? Thus we get 4, right? If you know that, you can go straight to here. I'm only showing the 4 squared because as we get to a couple of more complex examples later, it might be to our benefit to do that. All right, square root of 24, 24 is not one of my perfect squares. So what I need to do is find perfect square factors of 24. All right, so I have, 1, 4, 9, 16, 25, so on and so forth is my perfect squares. 4 is a perfect square factor of 24, and 4 times 6. The square root of 4 is going to be 2. The square root of 6 I cannot simplify, so square root of 24 equals 2 square roots of 6. Just like I was able to simplify each individual piece independently here, I could do the same with my example here, square root of 4x squared. I could break it up, right, just for illustration purposes, square root of 4 times square root of x squared. Or I can simply deal with this all in one. I don't have to write it like this, right? Square root of 4 is going to be 2, and the square root of x squared is going to be x to the first. Okay. Same thing here. I can do the same. Square root of 36 is going to be 6, and x to the fourth I could write as x squared, right? So x, or square root of x to the fourth, is going to be x squared. All right. The last one I'm going to write in a couple of parts here, right? So I've got the square root of 100, and I'm going to write x squared y squared times square root of x, right? X squared times x to the first is going to give me that x to the third term that I had over here, right? So when I simplify then from this first radical, we're going to have square root of 100 is 10, square root of x squared is x, square root of y squared is y, times the square root of x, which I cannot simplify, right? So that's one way you can break something down that's like that. Here in a little bit, I'm going to show you a way that's arguably a little bit faster, okay? So actually, let me come back. Let me show you that other way right away. So if I had something like the square root, and let's just keep it simple here. Let's say I have x, let's say to the 13th. Okay. Again, I mentioned before, if there's not an index written here, it's assumed to be 2. But let me put a 2 here for right now, just as a placeholder. So the long way of doing this, right, I need to break this up into essentially multiples of 2. I could rewrite this as x to the 12th times x to the first, right? And that x to the 12th is really the same thing as x to the 6th squared times that x to the first. So from this portion here, the square and the square, or the square root and the square are going to cancel. So this x to the 6th would come out times the x to the first, which is going to stay inside. Now, my faster way, right, or the Ferrari method, if you will, right? Again, my index here is 2. It's unwritten, but it's 2. So I'm going to ask myself, 2 goes into 13 how many times? Right, 2 divides 16, or 13, 6 times, with a remainder of 1. So since 2 divides 13 6 times, there are 6 x's that come out, and 1 remains inside from the remainder. Okay, so to that point then, if I had something like the cube root of x, I don't know, let's do to the 22nd, right? Actually, let's do to the 23rd. Right, I could break this up into multiples of 3, or we can do my quotient and remainder. So 3 goes into 23 7 times, with a remainder of 2. Right? So a little bit quicker, easier to simplify than some of the other ways to go about that. Right? The next examples here, we're going to increase the index. We're going to look at some cubes and some fourth roots. So the first example here, I have cube root of 27x to the 6th. So 27, is there a number times itself 3 times? It's going to equal 27, right? In this case, yes, there is. It's going to be 3 to the 3rd power, right? So the cube root of 27 is going to be 3, and 3 for the x to the 6th. 3 goes into 6 2 times with no remainder. Okay. Let's take a look at the next one. All right, I have the cube root of 16x to the 4th. So 16 is not going to be a perfect cube, but it does have a perfect cube factor, and that perfect cube factor is going to be 8. So I'm going to have 8 times 2 times x to the 4th underneath of my cube root here. Right? So the cube root of 8 is 2, so 2 is going to come outside. Cube root of 2 I can't simplify, so I know I'm going to have a cube root of 2 that remains inside. 3 goes into 4 for the x terms one time with a remainder of 1. So here I get 2x times the cube root of 2x. Okay? Let's deal with some decimals, right? I always say that fractions are your friend, and this is one of those times, right? I don't have a nice, neat, easy way to deal with square roots or cube roots or any roots of decimals. However, I know how to deal with fractions pretty well. So here, instead of 0.25 x squared under the square root, I'm going to rewrite that as, think of 1/4 times x squared, or x squared over 4. All right, remember that I can take a square root in a fraction, square root of my numerator over square root of my denominator, or if I have a product, square root of the first times square root of the second. These are some of the rules that allow me to break this down and simplify it. Okay, so here, if I simplify my numerator, square root of x squared, and my denominator, square root of 4, individually, square root of x squared is x, square root of 4 is 2, and I get x over 2, or 1/2 x. Okay, my next example, I have the fourth root of 81 x to the 6th. The fourth root of 81 is actually going to be 3. 3 to the 4th is 81. So fourth root of 81 is 3. 4 goes into 6 one time with 2 remaining. All right, so our next example is going to be the cube root of negative 64x cubed, y to the 6th, z to the 4th. Now with cube roots, we can actually have negatives, right? And in this case, the cube root of negative 64 is going to be negative 4. Think about it. I have negative 4 to the third power. Negative 4 times negative 4 is going to be positive 16. Positive 16 times negative 4 is going to give me that negative 64. Okay, so for cube or for odd roots, so fifth roots, seventh roots, so on and so forth, I can have negatives. For even roots, I cannot, for the same reason we can't have the square root of a negative without imaginary numbers. So here, the cube root rather of negative 64 is going to be negative 4. 3 goes into 3 one time for the x's. 3 goes into 6 2 times for the y's. 3 goes into z one time for the z's, with a remainder of z to the first left behind. So one of the things that we need to do is also come up with and memorize some of our powers of I. This is going to be really, really important in terms of our ability to simplify radicals as we go through this unit, right? So what I have here is a chart of powers of real numbers that we actually need to commit to memory, okay? So here we have, when I fill out this chart, right, what I'm looking at here is, 1 to the second power, which is 1. And actually all the first column is going to be 1. So in this second column, I'm looking at the number to whichever power, right? So here I've got 2 squared, or 4, 2 to the third, which is 8, 2 to the fourth, which is 16, and 2 to the fifth, which is 32. For the next column, I have 3 squared, which is 9, 3 to the third, which is 27, 3 to the fourth, which is 81, and 3 to the fifth, which is 243. Okay, so I'm going to let you guys fill out the rest of this chart, right? This is a chart that you should put somewhere, right? I do have paper copies of this, so if you want one to fill out to have handy, I can create that for you. But the values here that are not grayed out, okay, so you don't need to worry about these values that are grayed out, are values that are possibly or likely going to pop up in some of the worksheets and assignments that you're going to see, and or on the tests that we're going to have. I already talked in a slide earlier about the properties of simplifying radicals, right? So remember that we actually have a product and a quotient rule in terms of properties for simplifying radicals. So the nth root of a times b is the nth root of a times the nth root of b, and the nth root of the fraction a over b is the nth root of a divided by the nth root of b. So what we have is the ability to break this down in such a way that we can actually simplify some of our radicals, right? So again, a couple examples here, all right, and we did this already, but a few more examples. So the cube root of -24, right? Now these aren't going to work out quite as nice. 24 is not a perfect cube by itself. However, it does have a perfect cube factor, right? That perfect cube factor is going to be -8 times 3. I can deal with the exponents using my quotient and remainder on their own. Cube root of -8 is going to be -2. 3 goes into 3 one time with 0 remainder, and 3 goes into 5 one time with 2 remaining. So we're going to have 2xy times the cube root of 3y squared. If I look at the next example, the fourth root, right? 32 is not a perfect fourth root. However, 16 is a perfect fourth root. So here we're going to have the fourth root of 16 times 2, x to the fourth, y to the 16th. And when I simplify this, the fourth root of 16 is going to be 2. 4 goes into 4 one time for the x's, and 4 goes into 16 4 times for the y's with no remainders for either, times rather the fourth root of the 2 that was left over. When I deal with that third example that we have here, I can break this excuse me, into two parts. I have the cube root of 8x cubed divided by the cube root of 125. Cube root of 8x cubed, cube root 8 is 2, 3 goes into 3 one time, and the cube root of 125 is 5, because 5 cubed is 125. All right. So again, we can use the product and the quotient rules to break down and simplify radicals that otherwise would be difficult or challenging for us to simplify. Another thing to mention is that in this unit, we are going to look at your ability to break things down and do so with exact values, okay? I do not want decimals, right? We need to have the exact values. I want to see that you understand the principles of simplifying radicals, okay? Now, radicals with polynomials, right? Remember before I said that if I had something like a plus b, or excuse me, a times b to the nth power, that I could simply distribute that n to each, the exponent to each of those individual terms, because this was a product. And I can do the same thing if it's a quotient, right? A to the n over b to the n. However, I cannot do that if it is a sum, okay, or a difference. So like, you know, the freshman mistake is x plus y squared. This does not ever equal x squared plus y squared. Okay, so I'm going to show you here in a minute. It is essentially the same exact mistake, just from a different point of view. So in this first example that I've got down here, I have the square root of x squared plus y squared. This does not equal x plus y. The mistake a lot of people make is, oh, well, it's the square root of the x squared, which is x, and the square root of the y squared, which is y. No, that doesn't work because I have a sum or a difference here, okay? The only way that would work is if I had the square root of x times y, or x squared times y squared. Then this would, in fact, be xy, okay? But because in this example, I've got a sum inside of my radical, I cannot simplify that, so please don't. The only way that I can simplify a polynomial, here I have a perfect square trinomial. X squared plus 2xy plus y squared equals exactly x plus y, quantity squared. Now when I write this as a factored quantity squared, and my entire expression inside of that radical is factored, now I can simplify that, leaving me with the x plus y that comes out, okay? Again, you must be able to factor something completely before you can actually try to simplify that radical of a polynomial. All right, so 6-2 is multiplying and dividing radicals, and really it's going to be a continuation of the quotient and product rules that we just talked about. So I have a little bit of a warm-up here from essentially Alg 1 or geometry skills that you should be at least semi-comfortable with. All right, one thing that you do need to remember is that I need to completely simplify radicals before I combine them. So here, square root of 8, 8 has perfect square factor 4 times 2, so I get 2 square roots of 2 plus square root of 2. And 24 has perfect square factor of 4 times 6. Square root of 4 is going to give me 2. Square root of 6 I cannot simplify. Now I can combine these like terms here, right? Remember, for me to be able to add something, two terms, they have to have the same base and the same exponent. Well, one little trick for you here, the nth root of a is equal to a to the 1 over n power. Okay, so what I really have here, right, you don't have to write it this way, is 2 to the 1/2 power and 2 to the 1/2 power, right? I do have the same base and the same exponent. Here, I have 6 to the 1/2 power. It's not the same base. Even though the exponents are the same, they're not like terms, and I'm not going to be able to add them or combine them together. So again, the radicand and the index must match for me to have like terms so I can add them. So 2 square roots of 2 plus 1 square root of 2 is 3 square roots of 2 plus 2 square roots of 6. This is a simplified expression. Again, if I take a look here at the next one, 2 square roots of 5 I cannot simplify. 125 has perfect square factor of 25 times 5, right? Square root of 25 is going to be 5 times square root of 5, it's left over, and square root of 36 is 6. So 2 square roots of 5 minus 5 square roots of 5 is going to give me negative 3 square roots of 5 plus that 6. And again, if I take a look here at the cube roots, 16 is not a perfect cube, but it has a perfect cube factor. It is 8. And 54 is not a perfect cube, but it has a perfect cube factor, which is 27. Cube root of 8 is going to be 2. So I have 2 cube roots of 2 plus cube root of 27 is 3. So I have 3 cube roots of 2. 2 cube roots of 2 plus 3 cube roots of 2 is 5 cube roots of 2. Okay, so you guys did some addition and subtraction of radicals in Alg 1 and also in geometry. Here now, the other thing that's going to be fair game is cube roots, okay, and higher degrees. So the next thing I'm going to talk about that we did not talk about yesterday is, or in the previous part of the notes, is simplest form of a radical. So for a radical to be in the simplest form or to be in a final answer form, we need the following conditions to be met, okay? First and foremost, no perfect nth factors other than 1 inside of the radical, okay? No fractions inside of the radicand. So I need to simplify any fractions, because if I had, something in there, now I've got a radical and a denominator technically, and I need to rationalize that, all right? Which is really the issue for number 3 here, no radicals in the denominator. So we're going to have to be able to rationalize fractions, okay? So again, multiplying and dividing, product rule, the nth root of a times the nth root of b is the nth root of a times b, or vice versa. And the nth root of a divided by the nth root of b is the nth root of a over b, or vice versa. Okay, we are, for simplification, going to use this really in the opposite order. Sometimes we're going to have to multiply or divide things so that we can simplify something though. So these properties are going to be used in both directions, if you will. So let's look at a couple of examples, all right? And a couple of different ways I can go about a few of these. So the first one, I have square root of 3 times square root of 12. And I can ask myself, do I have any perfect square factors? And in this case, I do. So I have a square root of 3 times square root of 12 is square root of 4 times square root of 3. The square root of 4 is going to come out as a 2. Square root of 3 times square root of 3 is going to be square root of 9, or get 2 times 3, which is 6. It's one way to do it, okay? The other way I could do that is I could say also, right, square root of 3 times square root of 12. Well, what is 3 times 12? 3 times 12 is going to give me 36. Square root of 36 is 6. And I get the same answer in 2 different ways. So I can break down each of those smaller roots because they happen to have perfect squares as factors, okay? And then I had 2 values that I was able to combine, right, to make a perfect square factor, okay? Here you had an option. You could have simplified, or you could have multiplied then simplified, right? It's about as broad as it is long, tomato, tomato, okay? The next example, I have cube root of 3 times cube root of 9. Neither 3 nor 9 are perfect cubes, and neither of them have perfect cube factors. So what I can do then is use that property. I'm going to multiply these together. So when I have cube root of 3 times 9, I'm going to get cube root of 27. 27 is a perfect cube, and it's going to actually be 3. Okay. All right, same thing, next example. Here I have cube root of 4x squared y times cube root of 16x y to the 5th. Now 16 does have a perfect cube factor in it, but let me also take another look. 4 times 16 is going to give me 64, right? Is 64 a perfect cube? Okay, so hopefully you guys came up with the fact that 64 is actually a perfect cube. So here we're going to have the cube root of 64. When I multiply all this out, x cubed y to the 6th. Okay, I could break that down into smaller components, or I can do that, again, multiply it out and simplify it this way. So cube root of 64 is 4. Cube root of x cubed is x, and 3 goes into 6 2 times with no remainder. Okay, again, I could have simplified that and broke it down different ways. I could have broke 16 down into 8 and 2. Cube root of the 8 would have given me a 2 on the outside. I could have combined the 4 in the first cube with the 2 left over in the second to get another factor of 8, which would break down to 2, and then the 2 times 2 would give me the 4. Okay, either way, it's going to work out to the same result. Again, if I look at that last example, I have 4th root of 27x cubed y and 4th root of 3x y to the 6th. I'm going to multiply them together because I don't have any perfect fourth factors here. 27 times 3 is going to give me 81. X to the 4th, y to the 7th. 81 is a perfect fourth. The 4th root of 81 is 3. 4 goes into 4 one time. 4 goes into 7 one time, with a remainder of 3. So I've got a couple more examples for us to try, right? At this point, it's probably going to be helpful to maybe have a calculator sitting next to you so you can double check some things as you go through, all right? And again, here I've got two options. I have square root of 24 over square root of 32, okay? I can try and reduce, right, as a single fraction and reduce it. I can try to simplify numerator, simplify denominator. Sometimes one method is going to be faster than the other. Sometimes it's going to be the opposite, okay? So there's no right or wrong way here. But if I take a look and see if I can reduce, here I've got square root of 24 is going to be 4 times 6. Square root of 32 is going to be 16 times 2. Square root of 4 is going to give me a 2. Square root of 16 is going to give me a 4. And square root of 2. So if I think about this and I break it down into two things, the 2 over the 4 on the outside is going to give me a 1/2. Right? And if I look, I have a square root of 6 over a square root of 4. And if you remember off on the side, then I can write that as square root of 6. Sorry, not over 4, over 2, which is going to reduce to square root of 3. Right? They can reduce. I'm going to get a square root of 3 here in my numerator. Okay? So here I get square root of 3 over 2. All right? I was debating if I wanted to show that in another way. Why not? Let's do it. All right, so let's take a look here. If I chose to write that as a single fraction, 24 over 32, right? They're both reducible by a factor of 8. Here I'm going to get 3 over 4 is my square root. Can't simplify square root of 3/4. However, I can simplify square root of 3 over square root of 4. Square root of 4 is 2. Square root of 3 I can't, and I get 3 square roots, or square root of 3 rather, over 2. All right, so two different ways I can get the exact same answer. Again, one probably in that case not 100% easier than the other, but about as broad as it is long. All right, my next one I have cube root of 216 divided by cube root of 8. Okay, I can look at this in a couple of different ways, right? And I'll show you both. Cube root of 216. 216 is a perfect cube. Here, cube root of 216 happens to be 6. If you didn't know that, no big deal. I'll show you something else here in a second. Cube root of 8 is 2, and 6 divided by 2 is 3. Okay? The other thing I could look at here is, well, can I write that as a single cube root? So 216 divided by 8, all underneath of a cube root. 216 divided by 8, if you punch that in your calculator, is actually going to give you a 27. Cube root of 27 is 3, and I get the same answer again in 2 different ways. If I look at the next example, okay, I have a cube root of 27, I have a cube root of 4, right, my denominator. 4 is certainly not a perfect cube, and 27 divided by 4 isn't going to help me any either. So here, I'm going to simplify everything separately. All right, so let's deal with the numerator first. Cube root of 27 is going to be 3. 3 goes into 6 twice, no remainder, and 3 goes into 3 once with a remainder of 1. In my denominator, right, I have the cube root, and what I want to do is I actually want to break that down into essentially the prime factorization, right? 4 can be written as 2 squared. Okay. One of the things, and the reason I'm going to do that is because when I rationalize denominators, I want this to be the smallest denominator that rationalizes. So what I need to do, right, I have an nth root, right, and here I have some a to a power, right, okay, whatever that power happens to be. What I need to do is multiply by some quantity that's going to make this become an a to the n. What I need is for this power here to match this index here, right? So that they cancel one another out, and then I'm left with, you know, in my denominator, just a real value. I no longer have something trapped within a radical, right? I could do this with the 4, right? And I could multiply by square root, or cube root rather, of 4 squared over cube root of 4 squared. The problem is now I'm going to have something that later I'm going to have to reduce back out, right? If I do this with the smallest value possible, then there's a high likelihood that I don't have to reduce after. It's still possible, but it's likely I don't. Okay, so here I already have 2 to the second power. So what I need, right, is cube root of 2 to some power so that my result is 3, right? So what I'm going to have is the cube root of 2 to the first, right? So in my numerator then, I'm going to have 3x squared y times cube root of 2, or 2 to the first, over, and in my denominator I have cube root of 2 cubed. Cube root of 2 cubed, the cube root and the cube go away, and they cancel, and I'm left with x, or 3x squared y times cube root of 2 all over 2. All right, I've now simplified, I've now reduced that. Okay, again, when I have something like this, I want to try and make the index and the exponent match, and I want to do so in the simplest way, right? If you do it just by, you know, here I had 4 to the first, if I multiply by cube root of 4 squared over cube root of 4 squared, I would get a cube root of 16 in my numerator, which has a perfect cube factor of 8, right, which is going to come out then as a 2, and now I'm going to have a factor of a 2 over the 4 that would have come out in my denominator, and something that I have to reduce at the end. All right, so I want to simplify the process as much as possible, and sometimes it's going to take a little bit of problem solving, a little bit of thinking on your end to see which is the best or the most efficient way to achieve the goal of simplifying that radical. Okay, the last one here, I've got the square root of 12x squared over the square root of 3x. I could go right through and I could rationalize, and in this case it's a square root, so I can multiply by square root of 3x over square root of 3x. I don't want to do that, right? Reason being, I look at this and see that if I write, excuse me, as a single fraction, as 12x to the 4th over 3x inside of my square root, now I can simplify. I can do some reducing here. 12 divided by 3 is going to give me a 4, and x to the 4th divided by x to the 1st is going to give me an x cubed, right? Square root of 4 is going to be 2, and 2 goes into the 3 one time with a remainder of 1, okay? So, did already a little bit talk about rationalizing the denominator with this example here. okay? All right, but in terms of rationalizing the denominator, I want to go through, I want to find that value, and ideally the smallest value possible, such that I can completely reduce the radical in my denominator, okay? If I use a value that's larger than the smallest one, it's okay. It just means I'm going to have a factor left over that I now have to reduce out after I'm done, okay? So in terms of rationalizing denominators, let's go through, do one or two more examples. So let's start with a couple of square roots here. So first one, I have square root of 2 over square root of 3, right? Can't simplify this square root of 3, but I can't leave it there either. So because I have a square root, I'm simply going to multiply by square root of 3 over square root of 3. Again, I'll show you exactly why here in a second. I'll do this in 2 steps, even though you only have to do it in 1. My numerator, then I have square root of 2 times 3 or square root of 6. In my denominator, I have square root of 3 times 3 or 3 squared. Again, the 3 and the square cancel, and here I get square root of 6 over 3. So you can go straight from here to here. You don't necessarily have to show this step, but you can if you feel like you need to. Okay. In my second example, we have 1 over square root of 3x. Okay. Again, 3 to the first, x to the first, I can't simplify either. It's a square root, so I need the exponents that are each to the first right now to be second. So I'm going to multiply by square root of 3x over square root of 3x. So what I'm going to get here is square root of 3x over square root of 3 squared, x squared. And what I'm going to get then is square root of 3x over 3x. Now, one other thing that's also important, here you might be saying, well, why didn't you reduce the square root of 6 over 3, right? Or why aren't you reducing square root of 3x over 3x? I can only reduce different values that are either both inside of a radical in numerator and denominator or both outside of a radical. Think of that radical itself as, like prison walls, right? Everybody on the inside is stuck on the inside. They can't get out. They can't associate with anybody on the outside. Everybody on the outside can associate with one another on the outside, but not with anyone on the inside. It's a barrier that you can't cross over, right? So here we have the same thing. In terms of reducing, I can only reduce things that are both on the outside of a radical or both on the inside of a radical, but I can't cross over, okay? So let me take a look at this next example, all right? Here I have square root of x cubed over square root of 5xy. I'm going to do this in really in 2 different pieces here. If I look specifically at the x terms, right, I'm actually able to reduce some of the x's, right? I can't do anything with the 5 and the y in the denominator, but x cubed over x is x squared. So I have square root of x squared over square root of 5y, right? That simplifies things a little bit for me. Square root of x squared is x, right? Over square root of 5y, and that I'm going to have to rationalize. Again, it's a square root, so I'm simply going to multiply by square root of 5y over square root of 5y so that I get quantities that are going to cancel here, right? I'm going to skip right to the end here. We're going to have x square roots of 5y over 5y, okay? In my next example, okay, here I have the cube root of 4 over the cube root of 6x, right? There's nothing that's going to reduce here in terms of cube roots. So right now I have 6 to the first, x to the first. Breaking 6 down into a prime factorization isn't going to help me. It's not a number already to a power. Okay, so I'm going to multiply here by cube root of 6 squared x squared. I'm going to leave it that way for right now for a reason. Over cube root of 6 squared x squared. All right, what I'm going to then get here in my numerator is going to be, we're going to have 36 times 4, which is going to be 144. So I'm going to have a cube root of 144 x squared divided by a cube root of 6 cubed x cubed, right? Which is exactly what I want, right? 6 cubed x cubed is going to simplify simply to 6x. Now, in my numerator, I need to ask myself, I have a 144. Does 144 have any factors that are perfect cubes? Now, had I actually left it in the other form, and maybe I should have, in the prime factorization, let me call off to the side here, we had the cube root of 4 times cube root of 6. If I write both in prime factorization, I have a cube root of 2 squared for the 4 and a cube root of 2 to the first, 3 to the first for the 6. When I combine here, I have a cube root of 2 to the third times 3 to the first. Excuse me, this is 6 squared, so these are each squared, right? So let me fix that here. So this is going to be a 2 to the fourth times 3 squared. Okay, that's now going to work out the way I want. I forgot the square when I wrote that. Now, you would notice here that if I had this in the prime factorization, that same trick I used for the exponents still works. 3 goes into the 4 one time with 1 remaining. And 3 goes into 2 0 times with 2 remaining. So what I really get here is 2 cube roots of 18. Okay, so now when I take a look at this, cube root of 144 is going to be the same thing as cube root of 27 times, cube root of 8, excuse me, times 18 times x squared over the 6x. Cube root of 8 is going to come out as a 2 cube roots of 18 x squared over the 6x. The 2 and the 6 can now cancel or reduce, and I'm here going to get the cube root of 18x squared over 3x. All right. So there's a lot going on there. Again, I was just breaking that down in terms of perfect cube factors. And again, the perfect cube factors are probably not going to be as comfortable for you, all right, as perfect squares at this point. That's why that chart from earlier on is going to be really important for us. Okay, so please make sure, take a look, work your way through these. Some of them are going to feel really, really challenging at times, and you've got to work your way through it. It's kind of like riding a bike, all right? We just took the training wheels off, all right? So you're going to feel a little wobbly here for a little bit, okay, until you get a couple of these problems under your belt, until you start to feel comfortable with it. This is going to be a little uncomfortable at times, all right? So that's all I've got for this section, all right? Give some of the problems in 6.1 and 6.2 a try.